This integral is from 0 to infinity sine of mx over x dx, where m is given to be strictly positive. So we have to evaluate this integral. So we will integrate the function fz. Now we have to write the function in terms of z. Whenever you're having sine or cosine in the numerator, we know that we have to change the form in e the power iota mz. If m is given to be 1, if there is sine of x, then we write e the power iota z, right? If m is 2, we write e the power 2 iota z. So likewise. And denominator is same, just write in place of x as z. So we will integrate this function along c, where c is the contour which is indented at z equal to 0. Because if you put the denominator equal to 0, you get z equal to 0 as a point, only one point on the real axis. So we have the contour which is indented at only one point. So at z equal to 0. So c is the contour indented at z equal to 0, and we will integrate the function along the real axis from negative r to, this is having the radius as rho. So this is from negative r to negative rho, followed by this semicircle gamma, and this is radius as, this is rho, this point is rho, then from rho to r. And then we will integrate along this semicircle tau, right, which is in the upper half plane. Now as we do not have any points which lie inside the contour C, so I know that integral for the complete contour is equal to 0. So by Cauchy's residue theorem, this complete integration is equal to 0, because there is no requirement of the residue to find, because there is no point lying inside the contour, right? So of what we can calculate the residue, for what point we will calculate. So whenever you are having no point in the contour, in the inside of the contour, then that integration is, the complete integration along the contour C is 0 by Cauchy's residue theorem, right? So now I'm going to split this contour in parts, which are from, first I will integrate the function along the real axis from negative r to negative rho, right? And then along this semicircle gamma, then again along the real axis, and then again along the tau. So I'm going to write this as negative r to negative rho, because it is along the x-axis, negative r to negative rho, so the function should be in terms of x. So I'm writing fx dx. Plus the integral along gamma fz dz, right? Because gamma, semicircle gamma, along gamma you have to write the function in terms of z, the complex one. And then from rho to r, again x-axis, so fx dx, right? And along the tau again fz dz. So this complete integration is equal to 0. So I know that this always comes out to be 0, so only I need to find this integral. These two I will merge together later. So limit rho tends to 0 for the semicircle gamma, integral gamma fz dz, that is equal to, I know that the formula is minus pi iota, okay, I'm writing iota 0 minus pi, limit z tends to where the contour is intended for this semicircle at z equal to 0. So I'm writing z tends to 0, z minus z naught is 0, so I'm writing z minus 0 as z only, f of z. So this is equal to negative pi iota, limit z tends to 0, z into, what is the function? E the power iota mz over z. Cancelling this z, putting the value z here, you get minus pi iota. E the power 0 is 1. Marking this above equation as 1, this is your main equation. Now since 1 over z is tending to 0 uniformly as z tends to infinity, and 1 by z is a meromorphic function in the upper half plane as it has no singularity there. Yes? So by Jordan's lemma, I know I straight away write that limit r tends to infinity, integral over tau e the power iota mz. I'm having z in the denominator, so this 1 over z is tending to 0 as z tends to infinity. So by Jordan's lemma, this integration is 0, or you can also write f of z dz is equal to 0, just to put the value of 0 over here for that. So this is limit r tends to infinity, integral over tau f of z dz is equal to 0. So now letting in 1 r letting r tends to infinity and letting rho tends to 0, right? So if r is going to infinity and rho tending to 0, this will be minus infinity to 0. Then I put the value of this integration over here as pi iota minus pi iota. I have calculated already, and then this is from 0 to infinity. Now see, minus infinity to 0, 0 to infinity, merging these two together. So I get minus infinity to infinity f of x dx. And for the second integral, putting the value as negative pi iota. And I know that the last integration for that is along the semicircle tau is 0 already. So this is equal to 0. So this is minus infinity to infinity. What is fx? It is e the power iota mx over x, writing the function now in terms of x, dx, taking this pi iota to the other side. All right. Right. Now equating. Now I have to equate the parts. Should I equate real parts or imaginary parts? Because I need sign in the numerator, right, for the required result. So I need to equate the imaginary part. Because I know that e the power iota mx is what? Sine of, sorry, this is cos of mx plus iota sine of mx. So if I equate the imaginary part, I get sine of mx in the numerator for e the power iota mx. So this is minus infinity to infinity sine of mx over x dx is equal to pi. Very fine. Okay. Now this is your even function, right? So I can just take this integration as from 0 to infinity twice, right? So taking the integration 0 to infinity twice, because this is your even function, this is the result. Sine of mx over x dx is equal to pi. Now taking this 2 to the other side, I get now the required result. Sine of mx over x integration from 0 to infinity dx is finally coming out to be pi by 2. This is the final result.